a bit of an odd talk. Previously, up to last year, I would ask my hosts, what should I talk, and I give them a list, and they would dictatorially pick a topic. And last year, right around this time, I was chatting with a colleague who is at the boundary of information theory and signal processing, and she flat out told me, and if you know her, it doesn't surprise you, that she stopped following my work because I do too many random, disconnected things. So I was offended. But then I told my grad student every moment, instead of getting defensive, see what you can learn from a moment that you got offended. So I realized maybe that's a bad way of giving talks. They seem disconnected. So what I'm going to talk about is these disconnected applications that I've been talking about, and then try to give you a flavor why they're connected. So that will be 20 minutes. And then I will stop and then ask you for what you want me to talk about among those. I am guessing my host today might be as dictatorial to decide what that would be, but we can try. Okay. So I've been doing work on active sensing and active learning for a while, and it all started with 10 years ago. People started talking about cognitive radio, cognitive networks. And the idea was you're going to sense the bandwidth constantly, and if there is an empty spot in the band, you will just jump in and talk as a secondary user. And there, the problem that I got interested right away was the sensing modality you can control. You can focus on one frequency band and measure whether that frequency band is empty or not, or you can, basically look at larger chunks of bandwidth and see if those are occupied or not. Now, if you decide to look at a larger number of bands, you're going to collect more noise. So immediately I was interested in understanding, do I go for these very high resolution search with low noise, but then the information that I'm gathering is too low dimensional, or would I go for these large dimensional observations that collect a lot of noise? Which ones are good, when, in what scenario? So that sort of got me started. A similar problem when you want to understand, this is a collaboration with my colleague in Comp Sci, when you want to understand how our eye finds an object in a noisy background, your eye movement and the gaze, how much you're focused or you're looking broadly, is controlling the acquisition process. And it would be interesting to understand what is the right way to do this. How is the sequential nature of the problem comes into the picture. You can think about sensor selection and health monitoring. If I read off of all sensors that I'm wearing, my battery dies out rather quickly. So in face of cost of communication and cost of sensing, which sensors are most informative when? And it's sort of you can find more and more applications if you're doing remote sensing to find a target, the waveform that you're actually going to use. There's usually a bag of waveforms. Which ones are useful at which time. You can do it, we took it to the extreme, sorry, the image quality is bad on the screen. We took it to an extreme with Max Roginski and Lana Lazipnik. We thought sequential feature extraction in computer vision is again another example where you're looking for an object in an image and you can take different features, cheap features, which features are most informative along the way.
This is not bad, this is called
I'll tell you what the major difference between this problem and the rest of them will be. Exactly. But you'll see that computer vision in particular, we don't have as much noise. So the other application, it's a lot about handling the noise. And here you're given the image, you're stuck with the noise. There's no averaging that we could play in the other one. So in that sense, it's a bit different. And then you can generalize it to an active learning problem. You want to find a classifier, a separator of positive and negative examples, and you have an oracle that can give you for your example sample labels, and you ask yourself which sample I should ask for its label. So this is sort of all of the applications, and each of them has their own peculiarity. When I talk about it, I get sort of sidetracked. And so I thought I'm going to use the metaphor of a building. My family are all architects, so this is the most natural example. To map out how these problems are related to each other, and how I see them as facades of the same building. the core of the problem is what we started working on maybe 6-7 years ago called active hypothesis testing. This is a very well-known problem with a long history. So before I give you the history, let me just focus on the problem setup. So the setup is you have m mutually exclusive hypotheses, and let's say I'm in a Bayesian setup, so I have a prior about these hypotheses, and I have a sequential problem in which I'm collecting observations about this underlying process, and at some point I stop and I decide what is the, infer what is the true hypothesis that is running my world. Now, the active hypothesis testing is the caveat that you have actions where these actions control the conditional distribution of your observation that you're collecting. So now the problem is a bit of a control problem in the sense that I'm controlling this sequence of actions, and naturally the belief about what is the true hypothesis or what the truth. And the question is, how do I choose these actions? Okay? So that this is the very general setup. And as you can see, it's perfect for me because it's a control problem. I have to control these actions. But inherently, I'm not controlling any system. The system dynamic is constant. It's just the truth, right, which is hidden from me. I'm not affecting the dynamics of the system. So in essence, it's an information problem. I'm just controlling my own information.
Tau is a stopping time.
Tau is a stopping time, yeah. So in general, you can make it a stopping time, or you can say I'm collecting tau exactly, a sample. In the most general setting, you actually allow yourself to stop earlier or later. Okay, so the history of it, as I said, it's a long history. It goes back way before me. In fact, when we started looking at this problem, the most well-known and the most elegant version of special case of the problem is Wall's sequential hypothesis test. He's just giving a hypothesis test where the only action you can control is whether to stop or make a decision. What we were the most familiar with was Chernoff's 59 paper, where it's exactly the setup I looked at, but he's looking at an asymptotic analysis where he sends the number of samples to infinity and he looks at the error exponent. So in some sense, the first time I saw this problem, I thought, this is solved. I know this 59 paper, so I should be done, right? Now, in trying to understand what is the shortcomings of Chernoff's asymptotic analysis, we came across this set of work in the context of variable length channel coding with feedback. In particular, the work of Horstein in '63, and he poses it as a search problem. So I'm going to first describe you the search problem. It's a very simple problem. You have unit interval 0, 1. You have a point object hidden in this set. And your action is to test some subset of this unit interval. If the object is there, you get a signal plus noise. If the object is not there, you get noise. So what Horstein did, he came up with a strategy how to find this object. And this you can generalize to a two-dimensional case. You can do this remote sensing version. My favorite example is where's Waldo, right? You know, it's noisy. You want to find Waldo. Where do you look, right? So which subset you test. So this problem was a search problem, but you can show that it's actually exactly matched to a channel coding with feedback, where you have a binary channel, and I can go in more detail if this is what people are interested. So the two problems is the channel is a binary symmetric channel, and you're basically encoding real time, and you can stop at some point and decide what is the message. If you look at it from a channel coding perspective, immediately there is follow-up work to Horstein that have a very clear solution in a more sophisticated asymptotic than Horstein's the Chernoff's model. And basically the problem is solved. Unlike the fixed length codes and channels without feedback, this problem is very well understood. And basically there is a trade-off between the rate that you can transmit the message and the reliability you can get. And this rate reliability curve is known. And the best coding scheme has a two-phase nature. The first phase, you do an uncertainty reduction through your favorite channel code. After you know almost where the object is, you do an ACK-NACK phase between the transmitter and receiver to see whether this is the object or not. Okay? So what do you get out of this analysis? As I said, it's a very clean curve on rate reliability trade-off. So your coding schemes would achieve up to capacity C of this channel, and that is a function of the noise model that you have, and up to the reliability, the highest reliability this channel provides, and you can get a gain from the fact that you can stop early or late in terms of the exponent. So this was all known before us. So what did we do? We went to the hypothesis testing and tried to teach the active hypothesis testing literature something that we had learned from channel coding, and that relies on the following observation. In Chernoff's model, you have a small number of hypotheses and many samples to get the reliability to go to 0 with the fastest exponent. Right? So this is one extreme. You can pose another extreme where the number of hypotheses is growing, the resolution of my search in Horstein's context growing, and I'm interested in collecting enough samples to get to a reliability of fixed, let's say, epsilon reliability. Right? And there seem to be the schemes that do this do very bad here and vice versa. Unless you do this two-phase operation where the first phase, uncertainty is reduced via some good channel codes in terms of reducing the number of hypotheses, and then the second phase you're doing the ACK-NACK, which was similar to what Chernoff's solutions would look like. So we did the same thing. We take the active hypothesis testing, the most general form of it, and we showed two types of results. A converse that we showed the rate reliability, there exists a trade-off for all active hypothesis testing problems between how fast you can get the error to go to 0 versus how fast you can resolve the resolution of your hypothesis test. And you cannot do any better than this. And we got an achievability. Unfortunately, there was a gap. Right? So, and this gap in general could be quite large.
What's on the axis? It's the rate.
This is the rate, the information rate, and now I'm being vague, I can be more precise. It's log of m, the number of hypotheses divided by the average number of samples you would take. Right? And reliability is the probability of error, log of that divided by the number. Right? So these are the two things. And then the achievability by itself was interesting. In order to get the achievability, we had to define a new measure of distance between distributions. Let's say I have m distributions. They are going to be dictated by the hypotheses and which one is correct. And I'm going to measure the distance between them as an average divergence. And this was not known, but what we could see is that if you change the mutual information to exclude the effect of the I on the mixture distribution, you get a bump. And that was our achievability scheme. Again, if people are interested, I'm going to go in more depth where this guy comes. Okay? So this was the active hypothesis test. As soon as we had this, we could then come up with
How did this calculation to understand the gap?
Oh, no, the gap, we didn't understand the gap. We just understand the achievability, right? So, but there was a gap, right? And we still don't know. I mean, I can give you, if you give me a problem, I can tell you whether this is a good achievability or not, but we don't know how to put it. This guy.
So you can do that without normalizing, and then this becomes a part of verbal derivatives, right? And then you can learn it.
Yeah, basically, if you think about it, I want to create this symmetric divergence because I don't know which one of the hypotheses is correct.
You don't need to, that's what I'm saying.
I don't need to do symmetric, but I don't want to bias myself towards any particular one of them.
Yeah.
And anything that is not symmetric is going to naturally bias me
That's a
in some
conversation
sense.
you can do in the round table, but I claim that the bias actually is in the way.
definitely relative to the truth, you are biasing it. But I'm saying without knowing it, I don't know any other way. Yeah, but we can discuss other ways of doing it.
Okay, right. Sorry.
No, it's not. So then we were ready to just look at a particular setup and see how well we can do. The first setup we looked at is active learning, and again, I'm going to be very superficial to just give you a flavor of what the problem is. The problem is I have basically a separator that separates my examples. I have an oracle that can give me answers for each sample, and now I have to decide which sample to ask for the labels.
So you have two hypotheses.
Here it's a really simple binary classification when you do plus and minus, right?
Two hypotheses.
The hypothesis, no, I have m hypotheses,
Yes.
which is the shape of these functions. And if you're working with a particular setup, for example, it could be linear separators. So I find the best linear separator that separates my example.
What are the points represented?
The points are basically, let's say I have images. The points are these high-dimensional images. I submit them, and it comes back, yes, dog, no dog. Right? So that's the setup.
So dog and duck is two of your hypotheses or what?
No, dog and cup, yeah, exactly. So now, because I have binary, dog and not dog is my labels, and my hypotheses are the functions that are going to predict these labels. So one hypothesis is this curve. Are all the functions that can, in the future, predict what the labels should be.
What about function you mean?
A function on the space of the images, right? So I have a.
Okay, so this is basically a case of what we would call the partition-based, classification.
Yes, exactly. This is the training part of my
Let's
classification.
say it's a Hungarian school, right?
Exactly,
Partition-based
exactly,
classification.
But I don't-
In the binary case, you would have this picture as well as another picture.
Exactly, you're absolutely right. In the binary case, let's say I have one and this, right? But in general, I have a class of these functions, right?
So this is a data-driven approach to try to approximate the value decision service, right?
Yeah, this is a data-driven to just find the best function you can find. So we looked at a particular setup where we call it a realizable case. So we assume that there is a true function that can precisely tell you for every sample, every image, whether it's dog or not. And then this label is subjected to some random noise. So this is called a non-persistent noise model. So now if you send the same image to the oracle, you're going to get rid of the noise by averaging. Right? So this is the Bayesian setup. And the classes of functions we looked at, yeah, that's an assumption. That's a simple. Yeah, so this is the IIB assumption, you're right. But also on top of it, I'm assuming there is a noise that is exogenous to the labeling process, right? As opposed to a data-driven solution that says there exists no function that can predict this. What is the closest amount of one?
Is that the Novak from Harvard or where is it?
This is Novak from Madison. Rob Novak.
This is a question. Can I go back to the previous slide?
The image, this one.
So basically, you are testing for the hypothesis which curve you're using.
Yes, exactly.
So why not simply have hypothesis testing on each data point that is submitted to you? Why do I need to go through this?
So I want to find a classifier. If I have this function now, any other new example you send me, I never go to the oracle anymore. I evaluate it based on the separator. If it's on the left, I decide that it's a dog on the right. Right? It's the training phase before you try to train your classifier.
Following this one, I can do the following. I can go to a 5-dimensional space where you put my sample, okay? And I ask the oracle or whoever is trained there, and for every sample, tell me, forget your functions, just which of the objects is there, right?
Right.
Listen.
Go ahead.
Now, I take the points I cluster the points, okay?
Yes.
And that gives me a cluster, right? The boundary of those clusters are the decision surfaces.
Right. So that is called the supervised learning in the classical concept. This is, I am just doing it actively. I am saving some money in terms of going to the oracle. Right? At the end, I find a classifier The question is which way is the best way, and if I'm more careful, if I, for example, I have to pay for this annotation, then I benefit from carefully choosing my samples, because in your example, many of the samples fall in the middle region that are not going to help you find the best separator.
So the way this works is in different scales. I first get crude things, I compute the things, and I do iterative.
Yeah, so you could generalize my setup. I never said my actions are one action. You could batch them, right? It's the same.
Is it fair to say the reason you do this is because you don't want to consider all the samples that could have given to you in one shot?
Exactly. So that's why I have all the samples. I don't want to ask for their labels, because the labeling process in all of this is very expensive. You can go to the very extreme of unsupervising. You just never get labels. You just try to make sense of the geometry, how to separate these examples. And the other extreme, you ask for all the labels. I'm sitting in between that I want to just get as many labels that I need, not more.
So if you learn the boundary, you just want to get the samples close to the
Exactly, exactly. And there's a lot of information in that boundary, and I will talk about
So
it.
which class of classifiers have you considered?
That was what I was showing you. Oh, sorry. This is a classifier, the simple linear classifier that on the left is one, on the right and the other one. So you can think about my theta, my true hypothesis, is this threshold. And of course, in a real two-dimensional sense, this is a linear separator, right? It's the slope, not the exact value, right? It's not I draw it as a one-dimensional, but it's really a one-dimensional angle, right? And we could also consider, we did consider, these ended up being the simplest classifiers to learn, and we could do it very efficiently. The hardest one were these guys, though we call them disjoint functions. If the functions are such that they're clustered separately and they don't have overlap, then you really cannot save on different labels. You have to learn what is the region here, what is the region here, what is the region. So this ended up being the hardest, this ended up being the easiest. And that's what we first did. We did a geometric interpretation, given a problem, how easy or hard this problem would be. And what we could say, if we could identify globally rich functions, these are these guys, and we could say these are going to scale as well as log m, so we are actually in good shape. These guys were hard ones, and I can't say too much about them except for we couldn't get any log m behavior for these functions.
How does this relate to support vector machines?
So support vector machines is basically the training phase for finding the best vector that supports your data.
So what's the difference?
Oh, it's just actively. I'm actively sending samples, and I'm just,
So it's incremental?
It's incremental. So you have to do it in batches and just learn the support
So
for those.
is it better because if you deal with the whole data, you may get more efficient?
So I can't say it's better or worse, honestly, because I think it really depends on your application, right? If your data is cheaply labeled and you have lots of it, there's no reason to do this. If your label is expensive, then it makes sense to do this, right? And it's a very peculiar way of looking at it because I'm doing it incrementally, right? But yeah, so if the data is free, there's no reason. If labels are free, there's no reason to do this. So for example, for the internet, where you have tons and tons of random pictures of cats, it makes no sense to do this. But if you're actually doing medical imaging and you need a doctor in the loop to label your data, then it makes sense.
So there are two costs here. One is the acquiring of the acquisition of the data, and the other is the computing stuff.
Oh, I see. So you're going to be somewhat disappointed in this talk. I am actually very generous with computing. Things that I compute are often of exponential complexity, and I don't mind it. Right? My decoders are optimal, my encoders are optimal. So I apologize. I'm really interested in the statistical properties and not computability. But that's a very, very good question. So we had this with Colloquium, who is a learning theorist. It's hard to convince the learning theory people of this model because we assume the noise is well modeled and you're doing these active learning one by one, and they were like, you never know the noise. In fact, what happens is you know your label labeler is imperfect and is hesitant. By hesitant, I mean when you give it a hard example, it says, I don't know. Like you give it this, it says, I don't know if it's a cup or a dog, so I can't decide, right? Or it makes mistakes, it looks at an image and says it's a dog, well, it's really a cup with an image of a dog, right? So, and you don't know the labeler's model, right? You're not going to be able to give me a probability P of flipping and then do all your fancy stuff. So recently, and this would be a talk that I would give like in 2-3 months, but we have results that appear in NIPS where we consider this, and all we assumed is that the noise has trends. The trend is the rate of the error goes up as you get to the boundary. So, so can we actually extract information just from that kind of thing? And so what we have shown is that information can be retrieved in 2 ways. The labels, hopefully if they're not flipped, they're giving me information about the separators, but also the rate of error. So if I get a lot of inconsistency around these type of images, they tend to be the exact separators. So my function should be really good at those boundaries. Okay, so this was the active learning one. We went back maybe a year ago, 2 years ago, went back to the problem of active sensing of the sensors.
Just out of curiosity, how do you deal with the separability issue here? So you initially you take all the data,
Right.
at least using the set of or family of classifier using. It's not possible to perfectly separate them.
Yeah, so that's what I was saying. I'm looking at an easier case where there is a realizability that I am shoving my hand over. I said there exists in the class of functions I have, there is one that perfectly predicts the data.
That's a strong assumption.
That is a very strong assumption, right. And then all the imperfection is the labeling error, right? So and if you think about it, anytime we restrict our attention to a class, that's what we're doing. But in some sense, I'm trying to do something about the errors and
I just want to clarify.
yeah, no, absolutely, you're right. So on the noisy search side, we looked back at this problem that I posed, I sort of used as a motivation, sensing a small amount of frequency versus sensing a large swath of frequency and collecting different noise. So this problem is exactly Horstein's problem with the caveat that 2 things are different from his model. One is I might have 2 users present in the system, so I will get signals that are more complicated, right? I might have multiple targets and not just only one target. The other one is my noise changes depending on my strategy, right? And in Horstein model, he just had noise that was independent of what he was.
But the Horstein model, going back to this question, and I know you answered it, but I want to ask it again, you completely neglect timing issues and computational complexity.
Yeah, computational complexity, I'm completely open.
When you do this problem in your head, okay, actually now we know you use 2 types of processes. Processes that they are maybe broadband, but takes a lot of computation time. Processes that they are narrowband, they take very little time.
Yeah.
And depending on how quickly you can decide, you brain
So
decides.
that's an interesting thing. In these versions that we consider, the sensing cost is normalized. So one way to take this computational issue is to add a sensing cost depending on your action, to just run the Bayes rule. Right now we
And in the
just
sensing cost, you would include the computation.
computation cost associated with how Bayes rule is complicated. I mean, I'm doing a Bayesian setup, right? So in that sense, this problem generalizes Horstein, and basically it generalizes a class of problems that it's surprising how little attention they have gotten on a noisy group testing, where the noise of your group testing now scales with the group size. It's so natural, but I don't know of many where practitioners have looked at this problem. But theoretically, when the noise grows with the group size, what should my optimal grouping be? Right? So it turns out that we could do what we did in Horstein and generalize this group testing model, the solution to this group testing, to do something that we call searching with code books. So now I have multiple targets. So these code books are going to be 4 multiple access channels because now I have multiple targets, and again, if people are interested, I can go in detail what this model would look like. And that automatically will tell me that I have to do channel code, multiple access channel perfect feedback, something that is not very commonly studied because it's viewed as a irrelevant communication problem because you never have perfect feedback, and here our problem has perfect feedback because of our observation model. But also it has the peculiarity that the channel's noise is dictated by my code book. And again, this is something unusual for communications. It's like a channel state that whose state is coming from. But here the problem is fully solved. We managed to show that upper bound that we have is achievable with something that my collaborator invented called posterior matching, and I will talk about it with generalized forms. Now these were all the world state doesn't change at all. You can take the problem a little bit to its meaningful setup. Why would I monitor something that doesn't change? If the state of the world was not changing, I would never measure it. So in reality, we monitor things because somebody is going to walk in this room. If it wasn't, I would just turn off my sensors, right? So you basically can generalize the problem and allow it, for example, let's say the state of the system is hidden and varying according to some stochastic process, and you would like to observe the state of the system, but it's subject to noise and cost of sensing. Now, why would I want to track this system state? Is because usually I utilize it for something. So now I can add a little bit control flavor to it, is that I don't care about the state for state's sake, I care about the state to know what I can do with it. So you can generalize the setup. We have shown that this is actually equivalent, there is an equivalence between this formulation and a generalized tracking. So you can write it as a tracking problem where the control is all in is active estimation. Applications are the sensor selection. This is, sorry, my former postdoc Yoni Kafka's favorite example is the Malaysian airline. If you look for the debris in large areas, you had low resolution. But looking at small pictures gave you debris, but you missed most of the time you were looking at nothing, right? So you could do that. But of course, if the object was not moving, the problem would be simple, right? So you would just zoom in and find it.
So how far is this problem for the problem of sensor selection?
It's basically sensor selection is the same. But often sensor selections, what we have seen is the sensors have multimodality, so they're measuring completely different things, as opposed to this problem where you're really measuring subsets of each other, you just have additional noise. So if you think about this, this would be the Horstein if the object moved, right? So that's the same. Okay, so this is, I went a bit longer than what I estimated. So this is what, actually, I have two little cute stories that came out, and really, if I push it far enough, they're not very well connected to this building. One is the question of large-scale hypothesis tests. Often I don't have all my sensors in one location sensing everything. I have to pass information. So we have been looking at, can we do distributed information acquisition? When we have some preliminary work on distributed hypothesis testing with belief exchanges that we have done. It's very preliminary, and the techniques have very little to do with the active hypothesis
So what is
testing.
the case of large distributed
The nature of
position would be assumed by
I'm an old classic. I'm a little person. There exists a model that runs everybody's data, and everybody knows what.
How did you get it?
No, I don't. Yeah.
So the model-
We have had this.
So
Even my advisor couldn't answer your questions, so I'm okay.
It's all the existence, so you couldn't, right?
So you assume the existence.
The existence of a joint is a probability distribution for all observables.
Known to all.
And is there a result that allows you to claim the existence? No.
No, we
So
just.
Isn't it true that all the other things are claimed from the NP set?
That's true. I'm a Bayesian, so in a distributed setup, Bayesian is really shaky, right?
So
Even worse than that.
But anything does not necessarily assume single decision making.
Right. No, what I'm saying is that I'm Bayesian. Even the two users, I say they agree, even if neither of them know the truth, right? So the classic Blackwell conjecture, right? Like
This goes beyond that because
yeah, I understand this goes beyond that, but I'm saying I'm shakier than that.
Can I say why it goes beyond that? Because I even went to Arthur and said, yeah, you're going to ask him. Bayesian and decision theory, a probability theory, with two observers will never establish the rigorous.
Right, but what I'm saying is that it is known that, for example, two Bayesian decision makers, if they put 0 on the truth, they will agree on something. So everything I achieve is with respect to the agreement, we both agree on the wrong answer because the truth was excluded. So that's where
you can postulate a model, you can develop a theory, have mathematically provable, correct results, but you could never implement it.
So what we have done in terms of implementation here.
That's sort of false, what I'm saying.
Yes or no, because what do you mean by implementing it? If I believed in a real truth in the world, I cannot. But would I give you an example for where we have implemented it? So for example, it's often the case that you have sensors that measure in different directions. So for example, we have applied it for sensors that measure distance on the line to the object. And now if you have sensors that measure orthogonal directions, there is a truth where this object is, and they're measuring things that can be complementary, and this is a really good model to capture how these sensors can, in a distributed fashion, learn the location even though my observations are really limited in their own dimensionality. So in that sense, we have implemented it, and for that setup, it was a meaningful implementation. And the general theory, does it apply to everything? No, I take your criticism. But from an engineering perspective, no, what I'm saying is it's a fact of engineering life, right? I just take it that in that world, there is a truth, and I know the general side, right? So on the other end, we were, so this usually takes like 30 seconds, I love it. So it makes my 30 seconds stretch. So on the other hand, we looked at this sequential feature extraction. Maybe this is just as bad quality. So here I have a motorcycle driver, and I would like to find this object. And the state of the art is you will actually look at all squares, or I should say all rectangles with different aspect ratios, and basically run them through the image until you find the object. And we showed that if you do this sort of two-phase zoom-in operation, you test for a lot less areas, and you find the object with higher reliability. And this is true for cars and multiple objects versus one object. And the trick, as I said here, we didn't have much noise to play with, so there was no averaging going on. But we had this tree-like adaptive search that allowed us to prune what we are actually extracting. Okay, so this is lots of work with lots of people, so let me just first of all give credit where it's due. The active hypothesis testing work was done by my brilliant former PhD student, Mohammad Nakshbar, and he worked on connections to the noisy search and the active learning. On the noisy search, we worked with Michel Viguer at Paris Telecom, which is a university, it sounds like a company. Ofer Shivitz is the person who worked on posterior matching for Horstein, generalized it. So he and I worked on the noise, size-dependent noise with this former postdoc of mine, Yoni Kafi. I'm sorry, my slides are so beautiful on my screen. It's a pity. And on the learning side, I'm working with Colloquium, who's a learning theorist in CS. We have a brilliant PhD student, Sangbaya, who extended Mohammed's work was purely on the Bayesian setup. So Sangbaya is now looking at the setup realizable, but the noise model is not assumed. The moving stage is in collaboration with Andrea, in particular. The only things we know, which are very, very limited, are due to Seon Park, who looked at the binary erasure channel model for this. Just you know something perfectly or not at all. Nancy Rampalia is a PhD student who's working on it. On the distributed hypothesis testing, I'm working with Alan Sarwate at Rutgers, and on the feature extraction for computer vision, I'm working with Lana Lezebnik, and Young Silu and Anusha Lalita are the PhD students who are doing this. I'm going to acknowledge that when I was describing what the hell, why is my research so hard to explain to anybody, I had to be thinking various ways of explaining it. And I was talking to my mom, and she was working on this hospital that she's building in Shiraz. So she gave me lots and lots of schematics of this building. I didn't use them, it's just a mom thing, right? So anyway, so with that, I'm going to stop and ask you, I can talk about noisy active learning, measurement, noisy search, object detection with this spatial correlation. I think that might be better for roundtable. I don't have enough connections to this. And now with social learning, distributed hypothesis testing, I'm not going to talk about it. Wait for the, so maybe between these two we can do a binary classification. How many people want to see the active learning one? And the noisy search one? Even you.
I got one, okay.
No, because it has coding, I thought. Okay, so let me just open that one up. The learning one. How much time do I have? I'm sorry.
30 minutes. And even more if you want.
20 minutes? Okay.
Even more.
Okay. Just let me time myself. I hate it when people go over time, so that's the problem.
We don't have all the time for here. Trying to understand what the speaker wants to say.
Okay, good. That's perfect. Okay. So, okay, so let me just, I don't have much time. Let me just describe, the setup, as I said, is basically you have a unique function, hi, this is the easiest and realizable case, that describe your data in the plane. So xi is what we call instance space or sample space, and labels come from binary in this case, it could be general. And you select the sample x, and you ask a labeler to give you the label. In the classic setting, you see this labeler's label perfectly. And in our setting, it's a subject to a randomness. So when you submit X for labeling, you get a sample whose distribution conditioned on X, and the truth is going to be given to you. Okay? Or it exists. It's on the underlying truth that John doesn't like. This one exists, but we don't know what it is. No. You can ask a question. This is costly, right? The active learning, there has to be a sense in cost. So the special case is well studied. The special case is when you have a binary label and you add a binary noise, a flip with a probability p, you flip the answer of the labeler. You can think about it, x is submitted, h theta of x is given, but the oracle in the process of telling you flips the answer with probability p1 minus 2. This was first introduced by Rob Novak, and in this setup, he showed under certain conditions that the optimal policy order-wise is log m is the number of the samples, and log of 1 over epsilon is the order. So if epsilon is the error probability that you're going to tolerate, and m is the number of functions that you're going to try to look from, right? So this was the setup. What we did was to look at the setup slightly more general than what Rob was looking at. So I'm going to tell you that more general setup. And we came up with non-asymptotic lower bounds for the expected number of samples you need to resolve it up to an epsilon. And we came up with a query strategy based on our Jensen-Shannon divergence and provided achievability for this. In certain cases, these were, as I said, the easy function classes, these were matching. And then if I have time, which I doubt I will talk about case where you don't. So here, we assume that the person who's submitting the errors, this was in common with Rob's model, assumed that we know the noise that this person has. So let's say this is a labeler I have worked with for a long time, so I have decent model to believe this. As you can imagine, if you're doing crowdsourcing on the internet, you don't know who is going to do your labeling job. Maybe they're tired, maybe they're happy today or whatnot, so you want algorithms. The truth is still subject to some probability, but you want algorithms that adapt to the goodness of your labeling. Right? So that's the kind of work we do. So let's look at the problem. The problem, as I said, is slightly more general than Rob's. So you have a sample space X, and now all we have generalized is our labels are not binary anymore. They could be LRE labels, but we still are in a realizable set that there is a true labeling function. How would have predicted it, we know it. So I want to learn this labeling function, but all I have is noisy versions, and so this is the setup. Again, I'm going to look at the sequential version of this problem, where I allow myself a random number of samples. So I'm going to stop at a random time and determine what the true function is, and that's the function. And if I'm making a mistake, I get the function class, the function incorrectly, I'm going to forever incur a cost, which is the error that this guy is making, so that I'm going to penalize. Right? So the model is, this is the Noisian part, that I'm going to assume that the observation depends only on the label of the true data, and basically of course X that I submitted. So this is so this is how the dependency works. So this is the first attempt at the problem, and the objective is to find these submitted samples. Since I don't have time, let me just give you a sense. What we could show, these are non-asymptotic lower bounds, is that you need at least in expectation these many number of samples to resolve the problem. So let me just point out the important factors. Log m is at least, this is the number of samples you have, and log of 1 over epsilon. There is a constant that is going to basically blow up how many more than log m. This coefficient is related to the capacity of the channel that is induced by your f of l's, right? So you have labels and they get noisy clips. So this is, and the coefficient in front of log over 1 over epsilon gets to be equal to the maximum divergence that any two labels can be, right? So if I have two labels, I can distinguish which one is which by looking at the divergence between them. So this is C max of this channel. And the proof here relied on a dynamic programming characterization. So for those who use it, this is the advertising.
So this way the initial sphere includes
basically it's exactly, you're going to shrink. It's the shortest path computation. What we did is we guessed this function, modulo the constants added, and then we played with the dynamic program to get a comparison principle to find the exact number. And I'm putting the asymptotic results in terms of log m. If you remember, I have a prior that I'm defining on the m functions that I have. This is for the uniform prior. Our results are for general prior, so you can start with any bias. So that's where we can use .dp, so it's a little bit more.
And all of this depends that you know the aces.
So in this, this is a lower bound, so we give the guy everything, and we say you cannot do better.
But you know the aces. The function says.
Yeah, so that's what I'm saying. It's a converse. So I want to say, even if the guy knows age, if he knows everything, this is the.
Where is the type of the aces you have comes into the formula, or it doesn't matter?
No, this is a really loose formula, and it doesn't matter. No matter what class you have, you at least need these many. And this is because of the noise and the fact that your observations are not separable more than some. So even if functions are incredibly easy to discriminate, I'm adding noise to it, and this is what I'm going to have to do, right? So this is a worst case, best case scenario.
So you're starting off with m classes of functions or m specific?
No, a class of m functions.
Okay, and then you're updating the functions as you get more data, or?
I'm updating my belief about which one of the functions.
Okay,
as I
but
get more
still
data.
stick with the individual function.
Yeah, exactly. So that's why it's a non-asymptotic result. I'm not changing the number of functions or anything.
Does this Qi and Qk depend on age? Because that's those probability distributions, right?
No, so Q's are just how your labels get flipped. So let's say in a general non-biased setting, let's say every label gets flipped equally likely to one of the wrong ones, and with high probability stays the same. That would be a most natural case. But here we allow it to have all sorts of let's say some labels are more fragile than the other with the time.
So again, you need an assumption like that delta has to be finite.
This delta is finite. Oh, I see. Yes. Actually, that's it. Here we assume the delta is finite for this bound. The bound is true for delta infinite, so it's a useless bound. If delta is not, this is a technicality. It comes up a lot in statistics. The way you do it, you bound the delta. You look at samples within that bound, and then you treat the rest as low probability events. And you can fix this. I just didn't think it's useful for this talk. So this is the classic technique. So to make it work for Gaussian and stuff, you have to look at tails of the Gaussian. Okay, so in terms of achievability, and I'm just going to bother you with this one thing because it's cute. So let's look at how to solve this problem. And I'm going to pose an easier problem. Let's say I only take one sample, and I want to learn from that one sample what the truth is. Right? So just learning from a single sample, and see what we learn from this. So when I start, I have not seen this sample. My prior about the truth is rho. You take this sample, I get a observation, a noisy observation, which depends on different priors. I have to look at the mixture of this, right? So this is if basically label of this sample is L, I would get Q of L, right? And now I don't know the label of it, so what I will do is I imagine, this is the fictitious process, I think about query X, and I say if a query X is submitted and the truth is HI, label L will be produced. But then I know that this function HI is true with probability rho I, so I can think about the output distribution. What I will see is a mixture of these guys. So and I look at the Y, as I realize the Y, I have to update my prior to a posterior according to a Bayes rule, right? So this is Bayes rule. I didn't write it, but it depends on all of the parameters. So the real question is, what should X be for the posterior to be the most refined? I have learned the most about it. And it boils down to a very well-known problem, well-posed problem, due to Blackwell, that he says, I have two samples, X and X prime. Which one is more informative? So this is a special case of the comparison of experiments. And in Blackwell's result, actually at the same time Stein has similar result, the result is unsatisfying in the sense that Blackwell and Stein say if X is stochastically better than X prime, then X is a better experiment than X prime. What do I mean by stochastic? Meaning that this distribution is, what do you call it? Yes, it's stochastic. If X prime, the distribution under X prime is stochastically degraded version of X, right? That's for information theorists, then you will just take X, right? There's no reason to put a channel in front. But there really, in reality, you will never have these clean, one guy is stochastically worse than the other guy, right? So it's never that you have two sensors, one is always worse than the other. So it's sort of a partial answer. It's a sufficient condition too strong. So methods in literature for practice are either, what they do is they say, I'm going to find X that basically discriminates the most among these L functions. Because if it discriminates the most, posterior is going to be more sharp, right? So, and they often do it through a symmetrized divergence to not, sort of take any position. They're going to look at the prior. Another alternative, and where I got interested to look at this, is due to de Groot in 1962. He looked at it in terms of information utility, and I'm going to describe that. So let me first do the symmetrized divergence business. So you will have basically Q of H1 up to Q of Hn, and you want to discriminate among them the best. So you just find discrimination between these guys by taking the divergences between these guys. And you choose how you're going to discriminate, measure the distance between these collections. Information utility does differently. He says, and I personally, I don't know, I've never asked him in person, but I personally think he must have been influenced by this notion of uncertainty. He says, give me some kind of a measure of uncertainty that is concave and nice. And it measures, so this function V is on the prior. So you look at over the space of the distributions on M values and measure uncertainty. And now I will look at the expected reduction of uncertainty, and I'm going to call this a notion of information. Plug in V for Shannon entropy, you will get mutual information. Right? So this is what you will say. Okay, this is the Bayes operator. And so the most informative action, according to de Groot, is the one that gives you. But then he was shoving everything under the rug because what is the best V? It's unclear. In fact, and that's where our dynamic programming came about. If you write a dynamic programming equation, you get a functional characterization of a optimal V star that satisfies the fixed point equation of the dynamic program, and that's what we used to prove some of the results, even though there was no computational hope that we can solve. It's a shortest path problem, right? The V is the measurement of how useful this, because it's the shortest path problem, it's the total cost you're going to pay until you hit that state, the ending state. So the problem is time varying. If you give me prior row, it doesn't matter what time it is. It's sufficient. Right, so you say my expected value of V is going to be reduced for every action, so you minimize this reduction via the cost of it.
So you try to take the improvement zero, is that it?
Sorry?
You try to make the improvement in the dynamic dynamics zero.
No, you just say V star is exactly the solution to minimization of X, of all the possible things I could have done. And then the next unit is the same V star. Right? So that's, maybe I'm not understanding the question. So the information utility now gives me a converse and ability to do converse and achievability in a classic control sense. Because let's say I take the suboptimal stopping rule that I go up till the time that epsilon is known. So for sure I know all of my posterior has shrunk to be epsilon outside of 1 bit. Now, of course, any concave function that you would give me, and let's assume this concave function does not take too large of a jump, so I can handle it. So this function, when I evaluate it at a particular posterior, it becomes a stochastic process. Now, let's suppose I take a policy for choosing these experiments or these x's, sorry, this should be x. If these experiments, if I show that the information utility for this policy cannot be larger than some upper bound alpha, that automatically tells me a lower bound on how, because my uncertainty has to be reduced u of prior minus u of epsilon divided by alpha. Right? So that gives me a way to do converses if I do this upper bound, no matter what policy you choose, if you can come up with something. And that's our guess. Right? Of course, you have to do a lot of cleanup to get this argument working. On the achievability, you do the opposite. If I have some somehow find a function that can guarantee a lower bound for my information utility, then I know my information utility has to shrink u of prior minus u of stopping point. Now I know I am shrinking it at least by alpha, so the number of steps will not need to be any larger than the difference divided by alpha. So that would be this is why it's a very powerful method to do this. Okay? So I don't have much time. I'm okay.
Slide number 10.
Yeah.
If I understand correctly, you are given a sample, and you are basically doing a posterior based on that sample. But what does that mean? What should X be? And I don't quite understand the query that you're making.
So X again, remember, is I'm going to submit X to an oracle, and he's going to return a noisy version of HI of X, where I is the truth. Right? But I don't know which one, so I'm going to, given my knowledge, I can imagine what is the distribution.
But I don't understand the semantics. What should X be? X is given to you.
I'm trying to learn what is the best X to query. So if X is fixed, this is what
But
happens.
on the basis of what?
Based on the prior and my knowledge of QIs. What should be my best X be? Now that I know QIs, right, and I know what what my prior belief about them is.
So on the basis of the posterior, not on the basis of the prior.
Posterior will be a random. Prior is the fixed value. Posterior will be different depending on what I will see, right? So because Y is a random variable, so if Y is some number, my posterior will change according to base rule. If it's another number, I will have to write another base rule, right?
Let me try to understand this. Could I ask the question, what should X be after the first bullet? Yes, absolutely. You're right. If I had put it right here, then it would have been sensible probably. All right, that's all I did, because otherwise I'm not really sure what is the narrative.
Yes. You're right. I could have posed the problem first. Okay. Right.
So here the probability of flip to a different label will only depend on the actual query and the true label.
Exactly. That's the easy part. That's the easier problem. And the harder problem, which I won't get the chance, is when, for example, it's also dependent on your distance to the boundary, and we know how to solve that, but now the noise will depend on my query too, and I'm adding more noise as I ask harder questions. Right? Yeah. This is the easiest case we were expecting to get to. So let me just, okay. So what we try to do is come up with a query strategy. I'm just going to give you the strategy and not give its analysis. So just for those in the audience who might not have seen it, entropy, you can write the entropy of a distribution and the KL divergence between two distributions defined on the same space. So I'm going to use these. So what are the strategies? So again, I'm a cheater. Like if the problem gets hard, I think, oh, what do the practitioners do? They often do good things. So one of the first one is to do a sort of a worst case. Look at all of my distribution Q1 to Qm, which is the truth that I need to identify, and find the minimum discriminant between the two. And now submit an X, which gives me the maximum of these guys, right? So this is very clean. This doesn't require prior. It just purely looks at my distribution. And so it's a robust one. But as you can imagine, it's very expensive when M grows and you have no bias towards anybody, right? Because now I'm going to do pairwise distinction between all of my possibilities. And many of them are irrelevant because only one of these M is really relevant, and that's what you really want to discriminate. Another one is to to be lazy, and that's what a lot of the literature practically does, measure prior in terms of, measure prior in terms of, and I should have done this, measure prior in terms of the reduction in entropy, right? So I look at the entropy of rho and look at the expected reduction. The mutual information ends up being the expected reduction in uncertainty I have. And now I submit an X that gives me the maximized mutual information. And a lot of literature does. Another way of writing this that will be useful for me in a slide is to write it as an average divergence between each individual QI, QL, and the mixture distribution, right? So this ends up being the same, whether you like it as a divergence-based method or information utility method. And this is known, this way of rewriting it is known as the oldest we could find is due to Lin, and he calls it Jensen-Shannon divergence, which Sergio hates. I don't know if I
No, I'm not saying hate.
No. But I know Sergio hates, so he was very disturbed when we first called this extremely Jensen-Shannon because it's really a fancy name for mutual information, right? But he comes from statistics, so he was taking it as an average divergence. And it generalizes a symmetrized, non-Bayesian symmetrized divergence between two distributions f and g. You can always write it as half of f and f plus g over 2 and g and f plus g. It's not generalized in a Bayesian. Now what happens is, the problem with this is when you try to apply this maximum mutual information, something awkward happens. As if one of the functions starts becoming the likely winner, so your rho I starts being 1, this mixture distribution gets to be dominated by the ith term. So you're measuring the distance, you're measuring the average distances between these terms, but ends up being you're measuring the distance between q of hi and q of hi. So this quantity becomes 0, right? It becomes smaller and smaller. So it becomes very not very meaningful to use this. This is what, in coding you cannot really for finite number of terms. So what we did was say, okay, the problem is this mixture distribution, why don't we fix that? So we went in and carefully take an effect. So I'm going to write the divergence between M distribution. So now I'm writing it in a general sense. It's the divergence is the average divergence between QI and the mixture distribution when my own effect has been extracted out.
But you're still going to the point to take an average.
Yes, you have the averages. So I'm going to still be, if I know, for example, one guy.
Half of the problem of the singularity you described in the previous page is because you take an average, so you try to describe a sphere.
No. For that, it doesn't bother me here. Why I like the average is because of the other end. When all of the rho i's are equally likely, I would like this to be like mutual information. Because I have no guess, so I want to reduce. So I have a vector that is all equal, and I want to sharpen it. The fastest I can sharpen it is using an action that, that gives me maximum mutual information in one way or another, right? Because this is uncertainty and many other measures of how equal this vector is are going to act more or less the same, that they will try to half the options in some ways, and that's what this guy is going to give, the average is going to give, right? As opposed to Chernoff takes the worst case of these, and he will always be linear in the number of hypotheses because he's just going to have to go through all. Right? So this is a Bayesian generalization, just like mutual information was the L divergence generalization. This is the generalization of J divergence due to Jeffrey. So it's the difference between F and G is F and G, G and F averaged out, right? So this is where it is. And so the funny thing is, if you take this divergence-based approach, you come up with this very sensible measure of distance. Now, it's a very simple proposition to show that this has also an information utility meaning, which is the reduction in uncertainty when you're measuring uncertainty in terms of average log likelihood as opposed to the average log function, right? So that's sort of cleanly helps us do the converse and the achievability, and I'm going to give you a break using the thing.
The rho n goes to 1 in EGS.
So it becomes a rule. It distinguishes I from the second most likely thing that is going to get confused with it, right? Because the distribution is going to kick out. Among all of those guys, you have a mixture distribution. The second guy, if it's dominant relative to that, that's what you're going to take an action that separates the first and the second, right? And this is going to happen very naturally throughout the process. And so this piece, the information utility version, allows us to do this sort of achievability and converses, which I don't have time to talk about. I'm sorry. I've never timed myself so badly. I apologize for the Taras in the audience. Thank you.